Hey, welcome. In this video I'll introduce drift-ordered equations by deriving in a simple way a couple of the fluid equations reduced fluid equations from particle orbits. This is not a rigorous derivation, but it's intended to give you some intuition about what the equations mean and where they can come from. And so I'll show you how you derive a vorticity equation, for example, from particle orbits and from current continuity. And this follows on from a previous video on polarization drift, where it's shown that you could derive this from either orbits or from momentum. So the idea here is that we have particles along field lines. So if this is a magnetic field line, we have a particle which is moving as some kind of orbits around here, and it has a parallel components, which you can say along the unit vector in B. But it also has some drifts, and so this orbit is gradually drifting on a very slow time scale compared to the orbits. The orbits are fast compared to any kind of motion, but there's a gradual drift, and this perpendicular drift is V perpendicular, so this is a drift which is very slow compared to the fast gyro motion. And so we write the velocity of all species, so electrons and ions, as a combination of their parallel flow plus the perpendicular drifts. And the lowest order one is the E cross B drift. So E cross B over B squared. Plus then we have the polarization drift, so it's just proportional to the mass. And there we have a Q B squared, and here we have a D E perpendicular by D time, so that's the polarization drift. And then plus we have the magnetic drift, and there are a few different ways of writing this, but essentially it depends on the temperature. And then if you have a charged particle, so if this is an ion, this should be a minus sign, so a Q and a B, and then this would be like a B cross grad B, or a B squared, and this would be a magnetic drift. And this depends on the charge, so ions drift in one direction, electrons drift in the other, due to gradients of magnetic field. And then let's see, this is the polarization drift. And this is the case for all species, and so what we're going to do here is look at a simple model where we have ions and electrons, and we're going to assume that the ions are cold. That seems a strange assumption, since the whole point of fusion reactions is to make the ions hot, but this actually turns out to be reasonable in some cases, and it doesn't change the basic physics of what we want to look at here, which is the balance between the magnetic drifts and the polarization or the parallel flows. And so for simple models, it's quite common to neglect ion temperature. And so we're going to set Ti equals 0, so cold ion. And then the polarization drift, so this depends on the mass, and so you assume that the ion mass is much bigger than the electron mass, and so we neglect the electron mass contribution to this. So we neglect the electron polarization term, and so we can work out from this equations for the particle density and the current. And so we're going to write down the starting point for the equations is basically conservation laws. So we write down conservation of particles is just dN by dt plus the divergence of any flows, so n times v is 0. This could be u, I guess the fluid flow really. This just says that the total mass, so integrated this over the volume, is constant, and then we have the quasi-neutrality, so just divergence of J is equal to 0. It says there's no charge buildup in the plasma, because if there were, it would very quickly cancel out. And so you can basically start with these equations, and then we can put these velocities into it. And so each term in here we have to keep, say, these two for both ions and electrons. This one we keep only for ions, and then this one we keep only for electrons. And we can solve this equation, for example, using either ions or electrons, because n is electron density and is equal to ion density if this is true. It turns out to be easier to solve the electrons, because here we have dN by dt, and if we have and if we wanted to have a polarization drift, say for the ions, then we'd have a dE by dt in here, and so we'd have essentially on both sides we'd have a time derivative, and we couple the density to the electric field. If we solve for the electrons, then this velocity doesn't depend on the time derivative, and so it turns out to be easier to do this for electrons. And so we can just write down, so you have just substituted all the velocities into here. So we have the parallel part, we have the E cross B part, and we have the electron magnetic drift. And each of these terms is just a velocity times a density here, so this is the NE times the velocity. And the polarization term has gone, because we've been neglecting the electron mass. And so this gives us a density equation. This is often rewritten in a few different ways. So first of all, we'll take the E cross B equation, so here, this part here. So first we're going to write E cross B as in terms of the potential. So we write E cross B B squared, and this is usually just written as B cross grad phi over B squared. So we're neglecting any contribution from the A, so dA by dt. So there should be a dA by dt term inside the electric field, and that term we're neglecting, so we're keeping only electrostatic component, not the electromagnetic. So then this part here we can split into two pieces. So divergence of velocity times NE, and this is often split up as an advection term and a compression term. So we write this as we have B cross grad phi dot grad NE. This is coming from the advection part, and then we have a compression part, so we have an N. So NE times the divergence of the velocity. So this is B cross grad phi. And so this is advection, and this part's compression. So it's useful then to rewrite this part here. So we rewrite this compression part. We can use, so you can use that the curl of, so here we have phi times unit vector over B. So this you can split up as two components. This is phi times the curl of B over B plus grad phi cross B over B. And so you see that here you have here what we've got currently, so we've got a B over B and crossed with grad phi. Here there's a curl, so the divergence of a curl goes to 0, and so we can turn this expression into this one here. So we turn it into a phi times a curl of B vector divided by B magnitude. And so this expression here becomes, so that's the E cross B term, so written in terms of an advection and a compression term, and this form will turn up again for the magnetic drift as well. This is quite useful to write in this way. This term here, we have a B cross grad dot grad. This is an anti-symmetric operator, so if you swap the potential and the density around, you get a minus sign. And there's these symmetries here which can be very useful to try and preserve, and so there are particular numerical methods for trying to handle these Poisson brackets. We'll see them in a later video. And okay, next let's try and rewrite this term here. So take this magnetic drift terms here of a density and a temperature, so this basically gives us a pressure. So we can write this as this is a divergence here of a NT, and you can rewrite this in the same way as you did for the electric, the same way as did for the E cross B drift. You can write this as a divergence of the pressure, in this case the electron pressure, times the same factor, the curl of B divided by the magnitude of B. In this case you get some extra terms, So you get a divergence here. We have a PE over B, and we have a curl of little b. And this is assumed to be small, so that the direction of the b is assumed to be slowly varying, as is typically neglected. And so we write this term here, this is just including this curvature vector here. And so what we have here is an equation where we have the same, you see this kind of same pattern is appearing here. So we have this potential with the curl of B of B, and here we have pressure with the B of B. And this thing is quite often written as a special operator, so we just define something that's called kappa or C. So C of phi, for example, we define as just the divergence of phi times this factor. So phi times this curl of B over B. And this allows us to write the density equation in quite a simple form. And so here I've written out the density equation as an E cross B advection. So that's this advection term. We have a compression. And here we have magnetic drift. And then here we have basically parallel flow. And so this is the density equation. So then we can move on to the current continuity, so which gives rise to the vorticity equation. So we start with the divergence of J is 0. And then we just write that J is just En, and then we have Vi minus Ve, so for the ions and electrons. The E cross B velocity appears in both, of course, so that cancels out. And so the only terms that appear are in the ion equation we have the polarization drift, and the electron equation we have this same magnetic drift. And so we end up with these terms here. So we have divergence of, first let's put the polarization drift. So we have in the mass, this electric field, E cancels out, so we have E and then M I over B squared. And you have a dE by dt, so this is the polarization drift term. And then we have, next we have, say, the parallel current. So we have divergence of, and then B, and then J parallel. So this is just the parallel velocities of the ions and electrons. And then the other term is left is the magnetic drift, so the same as the density here, except now we just have the charge moving. So that was N times V was this part here. So now we have a minus times the electric field times the electric charge here. So we just have a minus, and the times here is ENT, where here ENT is just the pressure, so in electron pressure in pascals, for example, it's just given by that. And the whole thing is this is just divergence of current, and that's just equal to 0. So often this is rewritten because you have the E perpendicular is roughly approximately equal to minus perpendicular gradient of potential. This is neglecting, so minus dA perpendicular by dt. So it's neglecting the perpendicular components of the electromagnetic field. And so what you can write this as, and now this is the vorticity equation. So this is a simple two field reduced MHD model. So this equation from the vorticity you could derive from the momentum equation as well. So see a previous video about how this will happen. But basically this is the curl of the momentum equation from a fluid. And it can be written also in this way from a conservation of charge. And so we have the polarization drift current, we have a parallel current, and we have a perpendicular current due to the magnetic drift of the ions and electrons in this case. But more in general, we might have ion currents as well. And then this is complemented with a density equation. So you have again all these terms, and then what's missing here is a parallel closure. So we need something to approximate what these parallel flows are of the electrons, and the parallel current here. I'll cover that in a future video. Okay, thank you.